Perfect. Welcome everyone. Have you been in my classes before? Where are you all from? Martin's going to be next to me answering any questions throughout, so you can obviously type that into the messenger. So just let me know that everyone's happy with that and let me know where you're all from, because I love seeing what an international community we have. The UK, so someone is pretty close to me. Welcome, welcome. It's great to see you all. So today's lesson is on ionic and covalent bonding. We'll also be hopefully moving on to how we write the formulae of common compounds. So I'm going to share my screen and we're going to take a look. Is that sharing? Why is it saying it's paused? Resume share. Cool. Yeah. So hopefully you can all see that periodic table. Are we good to go?
I think so. Can we all just get a yes if you can see the iPad screen, please?
Okay, great. So here's our periodic table, which we know underpins the whole of chemistry. In it, we have all our metals, which we find on the left-hand side, and the non-metals, which we find on the right-hand side. Now, using the key, we can see that the bottom number found in the periodic table belonging to each element is the proton number, which I hope you remember from last week equals the electron number. And that's going to be really important when we look at bonding. So I'm going to pull out sodium in order to explain this further. So we can see from the bottom number that sodium has an electron number of 11. And we can write that configuration in a number of ways. We can write it like this, 281. So what does that look like? Well, if I draw it out, there's the symbol for sodium. We know that the first shell can only have a maximum of 2 electrons in it. Then after that, we can fill up to 8. And so if we double check, that brings up our electron number to 10. And then finally, one more electron here. So there is our electronic configuration of sodium. However, it has problems because it has that one electron in its outer shell. We say that it doesn't have a full outer shell, and really all elements, their only aim really is to be stable, and to be stable is to have a full outer shell. So what they want to do in this case is to transfer electrons in order to gain that full outer shell. And we're going to look at that now. So we've got sodium here, and now we're going to take a look at chlorine. If we look at that bottom number again, we can see that it has 17 electrons. So we can write that as this, 287. Let's now draw the chlorine electronic configuration. So that brings us up to 10 electrons, and then the final 7 go here. Notice how I'm drawing them quite carefully. You want your electrons in pairs at 12 o'clock, 3 o'clock, 6 o'clock, and 9 o'clock. In chemistry, we're very fussy about how we draw this. So if we look at this now, we can see that chlorine doesn't have a full outer shell, and neither does sodium. But what could happen is if I draw an arrow, we could see that a sensible thing to happen here would be for the electron in that outer shell of sodium to be donated to the outer shell of chlorine. And that's exactly what ionic bonding is. It is the transfer of electrons. And notice that that transfer of electrons always happens from the metal to the non-metal in this direction only. So if we were to redraw the new situation, we can see that sodium still has a very similar electronic configuration. Try and draw them more neatly than I'm drawing these. But because it's lost an electron, remember that electrons have, Zara, you want to, I kind of disagree with your chemistry teacher here. You do need to, if you have a look at diagrams, they do need to be in pairs. Just, I don't know, it's just good practice really to draw your electrons in pairs like this. So I'll have to disagree with your chemistry teacher there. So with our sodium, remember that electrons have a negative charge. So if you lose that electron, by definition, the sodium will have a positive charge, and we show that through the drawing of square brackets with a little positive charge. And that's really just indicating that that sodium has lost an electron. So it has now become what's known as a positive ion. It is now a charged particle. So what's going on with chlorine? Okay, so we're redrawing it exactly as we had it before. Here's the second shell, which is unchanged. And then that final shell, and notice that we have gained that 8th electron from sodium. So I'm going to show that using colours. That electron has come from sodium. It's really important that you show that it's come from the different atom. You can just use dots or crosses or different colours. That's up to you. And then in terms of the charge, because it's gained an electron, we know that it must have gained a negative charge. So the charge on the negative ion here is 1 minus. So we have sodium and we have chlorine. And that's really, when they ask you to draw an ionic bonding diagram of sodium chloride, that is your final answer. Do you want, I might just leave it there for like 30 more seconds so you can copy it down if that's what you're doing. Just let me know in the messenger when you're ready to move on. No, sorry, chemistry's, the more I teach, the more it just sounds ridiculous. You have to write the metal first. To Jennifer, I'm really sorry, you do just have to write NaCl. There's no way that they'd accept ClNa, even though, you know, really they should, but no, this is your final answer. The metal always comes first. This is the thing about chemistry. If you like following rules, and I do, this is why I really like it as a subject. If you're more artistic and you like being a bit more free and easy about stuff, I can see why chemistry wouldn't be your #1 subject of choice. And then one thing to point out is, as you can see, it's quite annoying having to draw all the shells. So actually, when it comes to the exam, you don't really have to draw all of the shells. You can just get away with drawing the outer shell. A bit like this, really, because it's that outer shell which is where all the interesting stuff is happening. So as you can see, I've simplified it now by deleting those inner shells. I just didn't want to confuse you. I wanted to show you how we arrived at our end result, but you can get away with just drawing that outer shell because that's actually telling you everything you need to know. So moving on to another example, magnesium oxide. So we have magnesium. Always refer to this periodic table. So it's here and it has 12 electrons. Oxygen has 8 electrons. So we're always using the periodic table here. Just going to make a little note before I forget them. So we can see that our electronic configuration for magnesium is 2 electrons into the first shell, 8 into the second shell, 2 into the final shell. Oxygen is 2 and then 6. So we're making sure that it all makes sense. So now we're ready to draw our magnesium oxide. There's our 2 electrons. Oh, I wish I was better at drawing the circles. My hand's so wobbly. Whoop. Okay, oxygen now. That's so messy. Okay, this is a nice straightforward example again. Hopefully you can see that oxygen needs 2 electrons, magnesium is happy to give away 2. So those electrons are going to be transferred from the magnesium to the oxygen. You'll probably get to a stage where you don't need to do this intermediate stage. This stage won't be worth marks in the exam. Don't worry though, if you're one of these people that does need to draw the intermediate stage, it's not an embarrassment. You just have to do exactly what you need to do in order to make sure you get the marks. That's not a problem here. If you can see it, perfect. If you need to do the mid stage, do it. So just to show you therefore, and I'm only going to draw that outer shell on magnesium because really we're just trying to show that it's full. So it's effectively this shell here becomes the outer shell because we've lost the final 2 electrons. So in terms of the charge on that magnesium ion, because it's lost electrons, it's lost negativity, it has a 2+ charge. How about oxygen now? Again, I'm just going to show you that outer shell. Being very careful with how I draw my electrons because it's gained 2 electrons from magnesium. This is how we're going to show it. Close the brackets and then the 2-. Do make sure that you draw square brackets as opposed to rounded brackets. Do make sure you write the charge on the ion in the top right hand corner. Like, people will say different things, but this is going to guarantee that you get the marks, okay? And so there is our final answer. That will be worth around 3 to 4 marks depending on your exam board in your GCSE or IGCSE examination. Okay, now we're going to get slightly more tricky with lithium oxide. So looking back at my periodic table, lithium is here, it's in group 1. It has 3 electrons altogether. We're still using oxygen, so we know it has 8 electrons. There's lithium. Here's oxygen. Okay, so I'm hoping you can spot a problem with this one in that lithium only has 1 electron to give away. So that electron is happy to transfer itself to oxygen, but sadly for oxygen, it's still only got 7 electrons and it needs 8. So in this situation, just draw another lithium. It's absolutely fine to bring in a second atom of lithium if it's what you need. We draw it the same as the first one. So it's introducing that final electron. And so you can see how they will both be full. Now to just draw the answer which will actually give us marks in the exam. Your lithium looks like this. It's lost that final electron, meaning that it has a positive charge. The oxygen, actually I'm only going to draw the outer shell on the oxygen. It has the original 6 electrons, but then it's gained 2 electrons from lithium. And so in terms of the charge, it's got a 2- charge, but then remember, we needed 2 lithiums. It's kind of up to you how you show this. Increasingly, I see that exam boards are accepting two versions of the same thing. Before, you could get away with writing a 2 here with no need for the second one, and that meant the same thing. It's totally dependent on what your teacher tells you that you need to do, whether you do that or you just draw 2 of them. I don't know which one you prefer, but they mean the same thing. Okay, so I'll give you a few more seconds to write that down, and then I'm going to give you an example. This is the most difficult example that you'd probably ever be asked, and I feel a bit mean asking you to do it, but I will show you how you do it. So just let me know when you're ready to see the example. Okay, can everyone have a go at drawing aluminium oxide? So write down aluminium oxide, and then I'm going to scroll back up and show you the periodic table so you can work out what you need from it. Ooh, okay, I'm going to help you here because this isn't cheating, but I want to make sure that everyone's starting at the same point. Aluminium has 13 electrons. Oxygen has 8, and Martin will write that into the messenger. I am going to make sure that hopefully everyone has enough time to do this because I don't want them to feel rushed. Because it depends, if you have to do that intermediate stage, it's going to take quite a lot longer. Okay, so aluminium, just going to draw the outer electrons, has 3 electrons in its outer shell. Oops, actually, sorry, I'm going in straight away, drawing the answer, I won't do that. Okay, so oxygen what am I doing? Has 6 electrons in its outer shell. So in terms of the transfer, 2 of the electrons will go to oxygen, but the problem is you've got that 3rd electron from aluminium that needs sorting out. So we need to draw another oxygen. But look, again, we have a problem because now oxygen is lacking. So that's when we draw another aluminium. Again, it's going to have 3 electrons in its outer shell. So now that oxygen is happy, but unfortunately, aluminium still has 2 electrons to give away. So this is why this gets so complicated. because you need that third oxygen in order to absorb those final 2 electrons. Oh, I hate how I'm doing these in different colours. Let's just tidy that up a bit. So hopefully you can see that, unfortunately for aluminium oxide, it needs 2 aluminiums for every 3 oxygens. So if we have a look at the final answer, we know that aluminium will have a full outer shell. This is really advanced, guys. Don't worry if you're finding it quite hard. We know that each aluminium will have lost 3 electrons, hence why it has a 3+ charge. We know that oxygen, again, will have a full outer shell. I think Martin's laughing at how horribly drawn my diagrams are. They're so horrible. I've got to redraw that one, it's gross. Oh man, that's better. Okay. Okay, so those electrons have come from oxygen. We know that it's gained 2 electrons, which is why it has a 2- charge. But in terms of how many of each we need, well, we need 3 oxygens and 2 aluminiums. So did everyone get that right? This is hard. If you can pretty much do everything else, then you're going to be fine. I've only seen this question come up once or twice in all the time, but this is like super hard. But hopefully you can see up here why we came to the answer that we arrived at down here. So just keep practicing, just keep looking at where those electrons will go and make sure that it's constantly full and you'll be okay. It would definitely be a grade 9 question, Zara. How would you do it without drawing out the whole thing? It's about balancing and juggling numbers. So if you're good at mental maths and you know that aluminium needs to give away 3, oxygen needs to absorb 2, what's the common denominator? 6. So then you can kind of multiply it up in your head. This is actually for me the most difficult example, Jennifer. So I would have another look at the previous example and make sure you're happy with that one. But for now, we're going to move on to covalent bonding. So I've got another periodic table here so that we don't get too bogged down with scrolling back up. So covalent bonding, notice this time we're looking at 2 non-metals, whereas before we had a metal and a non-metal. Hopefully you might find this a bit more straightforward. So let's start with our first example, hydrogen chloride. It's exactly the same situation. We are looking at the number of electrons in hydrogen and the number of electrons in chlorine. So in hydrogen it's 1, and in chlorine we have 17. So if I write out the electronic configuration, hydrogen it's just 1, chlorine we're going to do 2, 8, 7. And now the weird thing about covalent bonding is our pictures will look completely different. Whereas before we looked at square brackets, with covalent bonding, you're going to have overlapping circles, and I'll show you that now. There's our hydrogen, and it has 1 electron in its outer shell. Now I'm going to show chlorine, and it overlaps. Make sure you draw that nice and carefully, and you're going to show that it has 7 electrons in its outer shell. And there's the 7th one. And so hopefully you can now see that this is actually done. It's a very different example from our previous examples. Notice that we have 2 non-metals, but crucially the same thing is true. They are both now full. And if you're confused as to why hydrogen is full, remember that hydrogen only has 1 electron. So its first shell only needs 2 electrons in order to be full. If you now count up the chlorine electrons, we have 8. So that is why with covalent bonding, we say that electrons are shared, because indeed they are. Okay, I'm just going to move on again. Okay, water. So I've written its formula H2O. So hydrogen has 1 electron. We know this from the periodic table from the question before. Oxygen, we keep meeting oxygen. Just scroll back up, have a look at the periodic table. It has 8 electrons. So how are we going to arrange this? Well, you've got to try and make it symmetrical in your brain. So my way of doing that is to draw my oxygen in the middle, and you kind of get used to what these pictures look like. The same molecules come up time and time again, and you kind of get accustomed to what they look like. I'm going to show you a slightly different way of drawing it, which is equally correct to our example before. And let's start by showing what electrons we have. Well, we know that each hydrogen has 1 electron. And then we know that oxygen has 6 electrons in its outer shell. So I'm going to show 1 there, because we need to be completely symmetrical. So we've used up 2 electrons already. We've just got the final 4 to place, and there they're placed. And I just want to prove to you why this is correct. If you look at each of the hydrogens, they now have 2 electrons. Perfect, they're full. And if we look at oxygen, it has 2, 4, 6, 8. It is also happy, it is also full. So don't be sloppy with your work. You need to go back and check that you've got the answer right by counting up the electrons, because too many people I teach, I'll look at their answers and there'll be 10, 12, any number of electrons because they've been a bit sloppy. Do the electrons have to be overlapping a bit? Do I know what that means?
I think they have to be in pairs, but as Hazel said, you can draw it like she did in the first example, where the shells just touch each other, or they can overlap as they happen in this example. Both ways are correct, both ways will be fine.
Yeah, I think I prefer the overlapping one, it's a bit neater. Okay, methane now. So we're looking at a hydrocarbon. So let's work out how we're going to make this symmetrical. We need that carbon atom to be in the middle, and then we're going to have our 4 hydrogen atoms at 12 o'clock, 3 o'clock, 6 o'clock, and 9 o'clock. Make sure you label your elements. Hydrogen has 1 electron. Constantly looking at the periodic table. Carbon has 6 electrons. So remember, that means we have this electronic configuration for carbon. So the easiest thing to do here is to first of all draw all the hydrogen single electrons. And again, don't worry about which one's the dot and which one's the cross. It doesn't matter as long as they're different. And then for carbon, we know we have 4 electrons. And where will these go? Well, it makes sense if the electrons have to be shared, that each one goes into this little space here. It's very neat. And if we count them up, well, each hydrogen now has 2 electrons. And then if we count up the carbon atom, it has 2, 4, 6, 8. So it's very happy too, because they are both full. And so there is methane. The 6 comes from looking in the periodic table, and you see that it has 6 electrons altogether. Remember when we look at bonding, we're just looking at the outer shell electrons. So that's why I've written its configuration as being 2, 4. It doesn't have 6 electrons in its outer shell, it has 4. It's really important that you use the right number. If you use the wrong number, then you'll never get the electrons to balance. Simple molecular and giant structures, that's definitely a different lesson, for sure. That's a whole topic in its own right. Okay, this is hard now, ethene, so I'm going to show you this one. Right, so we have 6 electrons. It's very similar. So we have 4 electrons in the outer shell. Now, the reason why this is difficult is because we have our 2 carbons next door to each other. And then we've got to arrange our 4 hydrogens around those. It really only comes with practice, this. And then I'm going to add my hydrogen electrons. Remember, they each have 1 electron in the outer shell. And then at this point, I know that each carbon has 4 electrons. So looking at the left-hand carbon, we have 1, 2. Now, I'm not completely sure where the final 2 electrons should go, but I know that we need a bond between the 2 carbon atoms. So I'm going to pop them both in here. And I'm going to do exactly the same on the other side. So this carbon also has 4 electrons in its outer shell. And then we just need to double check. A lot of this is trial and error. So each of the hydrogens is happy because they each have 2 electrons in the outer shell. But what about the carbons? So taking the left-hand carbon, we have 2, 4, 6, 8. Yes, it's happy. It has 8 electrons in its outer shell. Double checking the right-hand carbon, 2, 4, 6, 8. Yes, it's happy. Notice the crucial thing here is that we have a double covalent bond. Look, you have 4 electrons in that overlap as opposed to the usual 2. So be prepared for this. Okay, and then I think we've only really got time for one more. So I think I'm going to get you to all have a go at ammonia, please. We'll give you the electrons in case you don't have a periodic table. I'm glad you're finding the lessons helpful, Zara. That's a really nice message. Okay, well done, everyone. So we're starting with our nitrogen. And I'm going to work out, well, how can I get this symmetrical with my hydrogen? So I'm going to have 1 hydrogen up here, and then 1 down here, and then 1 over here. The next step is I'm going to add all the electrons belonging to the hydrogens. And then for nitrogen, I know that we have 5 electrons in the outer shell. So we've got to have a sharing of electrons taking place. So they have to have at least 1 electron that they share. So there's 3 of them. And then this is a bit gross drawing it like this, but we're going to squeeze in the last 2 there. So now it's a matter of checking them. So I hope you're getting used to this. The hydrogens are very easily pleased. They all have 2 electrons in the outer shell. The tricky one now is nitrogen. So 2, 4, 6, 7, 8. Yep, nitrogen is correct. And there is your final answer. Did everyone get that right? Well done. It doesn't really matter where the hydrogens are, like try and get them symmetrical. You can see that I'm not a great drawer, but the person marking my paper will know that I understand that everything's supposed to be kind of equally placed. So well done everyone that got that right. It's really, really good. I'm going to end here, just have another look if you're a bit upset about the aluminium oxide one, just practice drawing that again after the lesson. Make sure you work out how many electrons you have in the outer shell. That is key. And then you'll be able to work out how many of each atom you'll need in order for them to both be happy with their full outer shell. So did everyone find that helpful? My pleasure. Glad you're finding it helpful. Who's joining us? Who's joining me tomorrow in bio? Yay, looking forward to seeing you all then. Okay, everyone, have a great day. Yeah, and I hope you're all doing really well.